Have you ever wondered what eigenvectors and eigenvalues really mean? Just beyond the formulas. Why do they show up everywhere in machine learning from PCA to deep learning optimization? Let's break it down visually and intuitively once and for all. So imagine you have a matrix, a transformation that stretches, squishes, or rotates space. You pick a vector, apply that transformation, and usually your vector changes direction and length. But there's something special. Some directions don't rotate at all. They only stretch or shrink, and they keep pointing the same way. Those directions are called eigenvectors. Now, for every eigenvector, there's a number called an eigenvalue that tells you how much that direction got stretched or compressed. For example, if you see in this equation 1, you can see that if we apply a transformation A to a vector B, then it doesn't change direction. It simply stretches or squishes. In this particular case, the transformation A acts on the vector and just multiplies it by a scalar lambda. No rotation, no direction change, just scaling. In this particular case, we say this vector V is an eigenvector and the value lambda is an eigenvalue. We'll take another example. Imagine a transformation that doubles everything along the x-axis and halves everything along the y-axis. So in this particular case, we take AV1 equals to 2 times V1 and AV2 equal to 0.5 times V2. Here, V1 and V2 are eigenvectors, while lambda 1 equal to 2 and lambda 2 equal to 0.5 are eigenvalues. Basically meaning that x-axis and y-axis directions are eigenvectors and the scaling factors lambda 1 and lambda 2 are eigenvalues. Geometrically, eigenvectors pointed along the neutral axis of a transformation. They reveal how space gets stretched or squeezed. The longer axis of the ellipse corresponds to a larger eigenvalue. And that's where the transformation stretches space the most. Eigenvalues and eigenvectors aren't just math. They power some of the most fundamental algorithms in machine learning. In principal component analysis or PCA, the eigenvalues of the covariance matrix gives us principal directions. The directions where data varies the most. The corresponding eigenvalues tells us how much variance each direction explains. In optimization, the Hessian matrix's eigenvalues tells us how curved the loss surface is. Larger eigenvalues mean steep directions and smaller one means flat regions. This simple yet powerful concept forms the backbone of so many machine learning algorithms, and now you understand exactly why. So if you're enjoying this Math for Machine Learning series, don't forget to subscribe and let's keep unfolding the math that powers AI. I'll see you in the next video.